Okay, fundamental theorem of line integrals is the topic of this video. Here's the statement. Um, the line integral of a vector field, which happens to be the gradient of a function of a function of several variables with respect to a path, the path, is simply evaluating the anti-gradient at the end point minus the anti-gradient at the starting point of the path. That's it. So this is equivalent to the fundamental theorem of calculus in Calc 1, where once you have the antiderivative, now in this case we have the anti-gradient, then all you have to do is plug in endpoint, initial point, subtract, and voila, that's it. You don't have to do anything else. This can save you a considerable amount of time and effort. It is a good idea, however, to do integrals initially both ways. The regular way, which would be to find the derivative of the path, dot it with the vector field, and then do the integral, and then do it differently by finding the anti-gradient of the vector field, and then plug in the endpoints, and that's it. And realize that we end up with the same answer. Our examples, at least in two of our examples, we're going to do it both ways. Yeah. So if the vector field happens to have an anti-gradient, which not all of them do, then F, the vector field, is called conservative. So we have a new definition. Let's label this as a definition. Yep. We are defining what the adjective conservative means for vector fields. If it has an anti-gradient, then it is conservative. If it doesn't have an anti-gradient, then it is not conservative. So not all the vector fields are conservative. Not all of them have an anti-gradient. Yeah. This is an informal statement of a theorem. Under nice domains, so assuming that everything is continuous and some derivatives are continuous and everything is smooth, there's no interruptions, sort of like the equivalent to vertical asymptotes and such. So this is very informal, but please find this kind of theorem in whichever textbook you may be using. Oftentimes, though, these theorems are broken up into parts. Not all of them, not all of those items consolidated into one. They may have two in one and another one in another theorem and so forth. So I'm consolidating theorems into one, which makes this a little more informal. And that is okay because this is supplementing what you are reading in whichever textbook you may be using. So thanks to this, all we need to know is the endpoints. We don't even care necessarily about the path we are going to be taking. Whichever path we go, so whether you go crazy with loops and going around and coming back, all you have to do is know what the endpoints are, plug in your set. That is called, whenever that happens in general with a vector field, that situation where it doesn't matter which path you take, you're still going to end up with the same answer, is what we call independence of path. So if you have a vector field, which is independent of path over some domain, that's one situation we can have. That is equivalent under nice conditions, and this is why this is informal, to having the line integral being equal to 0 for any closed path. So if you go out and come back, you're still going to end up with 0. Why? Because you may end up with a number going one way, but then when you come back, you end up with the negative of that number, or the opposite of that number, and adding them together, you end up with 0. And this is equivalent to this, that f is conservative. So if f is conservative, then you have that any line integral over a closed path is going to be 0, which also means that independence of path happens when you integrate f. So all of those three are equivalent under good conditions. Conservative, independence of path, 0 for closed paths. Yeah. All right. So one question that we can ask ourselves is, how do we know a vector field is conservative? In other words, whether it has or doesn't have an anti-gradient. Instead of antiderivative, I'm calling it anti-gradient. Well, if there's an anti-gradient, that means that there's another function, little f, for which this guy, p, would be the derivative of f with respect to x, and this would be the derivative of f with respect to y. So consequently, if we take the derivative of this with respect to y and the derivative of this with respect to x, we should have equality because they would come from the same function. So py would be equal to qx. This is the situation. Okay, so we want to know whether f, which is made up by p and q, comes from a function f of x, y, but this is the output of this function is one-dimensional. The output of this function is two-dimensional. So we are differentiating between the two. So if this comes from this function, that means that p came from, I'm going to circle this because let's think of this as one unit, from taking the derivative of this f with respect to x, and the derivative of this same f to get q with respect to y. Now, so those two come from the same one function. If that is the case, that means that if we take the derivative of p with respect to y, we're going to end up with p sub y. But that also means that we end up with the derivative with respect to x and the derivative with respect to y of f. If we take the derivative of this guy with respect to x, that means that we are taking the derivative of f with respect to y and then with respect to x. But there's a theorem that says that under nice circumstances, those two are going to be equal. So there. So this is the test we can perform to figure out whether this guy is conservative or not. In many, many problems, we ask our students to check whether something is conservative or not, and this would be a valid method. Excuse me. It is a good method. Personally, and I'm speaking for myself, personally, what I do oftentimes is try to find the antiderivative or the anti-gradient. If I find it, that means that the vector field is conservative. So I'm going to write that down. Personally, okay, I try to find f, which is the anti-gradient, comma, the anti-gradient. If we find it, and in my experience, it's fairly quickly, fairly easy, then f is conservative. If we cannot find it, then we perform the test. So I'm a little bit of a risk taker. This tells the viewer that I'm a little bit of a risk taker because I just try to find it. And if I cannot find it, then I still have to do the test. See, if you do the test, you know for sure whether your given vector field will be conservative or not. I kind of guess that they are, and so I try to find it. If I find it, boom, I don't have to test. But if I don't find it, then I don't know. Not being able to find something doesn't mean that that something does not exist. So then I have to figure out whether this exists or not by performing the test. So again, that is just me personally. I think both methods are good. The only difference is that in one of them we take a risk, and the other one we don't take a risk. Okay, so let's do an example. Example 1, and we're going to do this using two methods. So let's say we have a vector field f of x, y, which will be x minus y, comma, y minus x. All right, and the path C is going to be given by r of t equals, so we're going to parameterize the sine function t, t, this is a t, comma, sine of t. So the path is just your regular sine function. Oh, I didn't mention the domain. We should mention it. So 0 is less than or equal to t, less than or equal to 2 pi. So just the first cycle after, starting at x equals 0, this point is supposed to be right on the origin. Okay. What we want to do is to evaluate the line integral on this path of the vector field. Now, I haven't shown you how the vector field behaves. If x equals y, then those two numbers are going to be 0. So this is the path. And now the vector field. Okay, so on this line, there's no wind, there's no flow. And the farther away we are from this line, see, this number will be exactly the opposite of this. So if this is positive, then this is going to be negative in the same magnitude. So all the vectors we're going to have are going to point, so positive, negative, to the right and down. So diagonally down right, or diagonally the other way. So all the vectors are going to either point this way, all the vectors that are not on the y equals x line, or they're going to point the other way. If x is greater than y, then we're going to go to the right and down, diagonally, perfectly at 45 degrees. And the farther we are, the longer the vectors will be, because the farther we're going to be from, there's going to be more x than y, and so forth. Okay, so the question is, as we go, we always go under this line. Yeah, because the slope here happens to be, let's see, derivative of sine is cosine of 0 is 1. Yep, so the slope here happens to be 1. Yep, so I'm going to combine the two down here. So there's a line. And the graph actually doesn't cross this. It is tangent to this line. The graph of the path comes down, goes up, and then we have again 45 degrees going this way. And the vectors are going in this direction. So the question is, and the farther we go, the longer they are. So the question is, what is the work if we have this vector field if we take this path. Okay, so let me draw a line here. And this is going to be the integral from 0 to 2 pi of the field, which is x minus y, except we're going to use this for x and that for y. So remember, the path tells you the x and the y. This is x and this is y. So t, because that's x, minus sine of t, because that's y. T minus sine of t, comma, because we have a vector, comma, and then the reverse. Boy, sine of t minus t, close the parenthesis, so this is a vector, dotted with the derivative of this vector, which is 1, comma, cosine of t. Close the parenthesis, so this is another vector, dt. So remember, that is the way we figure this out. F dotted with r prime dt. So hopefully this is kind of crunched into a small column, then hopefully that won't create too much of an issue. So we multiply t you know what, it kind of does. Let's just move this to a new page where there is more. So I'm going to rewrite this on a new page. So we have the integral from 0 to 2 pi of t minus sine of t, comma, sine of t minus t, close parenthesis, dotted with 1 cosine t, close parenthesis, dt. So we are dotting those two. That is equal to, from 0 to 2 pi. So first component times first component, I'm going to put a bracket. So t minus sine t. And then second component times second component, but we're adding, there's no comma. Big deal, big difference. Because now all of this will be a scalar function. So sine of t times cosine of t, sine of t, cosine of t, minus t cosine of t, close bracket, dt. All right, so now we're integrating all of this. Integral of t is easy, t squared over 2. We're going to plug in 2 pi. So this is going to give us 2 pi squared over 2 minus 0 squared over 2. Now let's think about this, each one of those terms. Sine of t is really, your regular sine function. There it is. And if we are integrating from 0 to 2 pi, whatever this integral is going to neutralize the other part here. So those two are going to add up to 0, positive, negative. So that's going to be 0 because of the shape and the interval over which we are integrating. That's going to be 0. That's going to be 0, but let me explain why. Okay, so we're evaluating the integral here. Here we haven't evaluated the integral. We know from trigonometry this is really the sine of 2t over 2, again from 0 to 2 pi. Minus, okay, I'm going to do a little bit of side work, t cosine t, down here. Side work. We want to find the integral of t cosine t dt from 0 to 2 pi. And we're going to use integration by parts. Remember, if we said u equal to t, du equals dt. And if we set v, actually dv, to be equal to cosine of t dt, then v equals sine of t. And we're closing the bracket. So by parts, we multiply those two, t sine of t evaluated from 0 to 2 pi minus the integral of sine of t dt from 0 to 2 pi. Okay, so that is going to be 2 pi sine of 2 pi minus 0 sine 0. And this integral, again, by the same argument we had earlier, will be 0. You know, we're integrating just sine from 0 to 2 pi, so we get 0. And sine of 2 pi, again, is 0. So the whole thing, we're doing all of this to get just 0. So this is really 0 minus that, 0 minus this 0. So the whole thing is 0. Okay, so that integral, but you have to show, you know, some of the work. So this comes from that. That's going to be 0. And now let's think about this. This is a sine of 2t divided by 2, which means that the amplitude gets down to half. But we have a sine function with the frequency of 2, so 2 full waves per 2 pi. So again, I'm just going to graph this quickly. So we got 1, 2 of the same thing, positive, positive, negative, negative, and there's symmetry across. So the whole thing is going to be 0. So this is 4 pi squared over 2 minus or plus, because those two zeros we can ignore since they're not going to affect the value. And that's going to be 0 because of this argument, this geometric argument. So the final answer is 2 pi squared. Now this was an easy problem. And look how much we were involved in the integration process. You know, if we were not very adept to integration or very quick with integration, we would have to do the antiderivative of this, which is cosine, plug in 2 pi, plug in 0, realize that we end up with the same number, subtract them, end up with 0. Here, we can either do a change of variable because cosine is, after all, the derivative of sine. So you're going to end up with, if we did that, instead of this trigonometric identity, we would have u du, which is u squared over 2, but we're going to plug in sine of, as soon as we change the variable, sine of 2 pi is going to be 0. Yeah. And even then we got to be careful because from 0 to 2 pi, the function is not 1 to 1, which means we actually have to be a little more careful with this. And here, we did the work. So there's a lot of things going on, a lot of parts of this to get to this answer. So this was method 1. I did not emphasize that, but back here we can, when we started setting it up, we can just call it method 1, and we can just write 2 pi squared. Yep, that's the final answer, but we have to write a note. See, well, in my notes it says page 4. In these notes that I'm writing, this was page 3, and where I did the work was page 4. Okay, so there it is. And this is method 1, which is by brute force, or I would call it brute force by actually doing this. Let's redo the problem. So let's call this method 2. I call this method 1. I'm going to copy down the path. R of t equals just t and sine of t. It is important to establish the domain, and then the vector field x, y equals x minus y, comma, y minus x. Now, one of the things we may ask you is to find whether this is conservative. If this is not conservative, we cannot, I repeat, use method 2. By the way, I'm calling this method 2 arbitrarily. Yeah. That doesn't mean that the rest of the universe calls this method 2. I'm just calling it 2 because that was the second one I'm going to do, but not because people call it method 2. Some things are universal and some things are not. So anyway, the test is, well, if this came from a source function, and then this was the derivative of that source function with respect to x, if we do the derivative with respect to y of this, we end up with -1. That source function, not this one, but some source function, whose derivative with respect to y gives us this. Well, that's what we want to find out. If it did, then when we find the derivative with respect to x of this guy, which is -1, those two should match. Since we do have a match, that means that we do have a source function that produces this function when we do the gradient. Okay, so this is the test. There is one. Now, let's find the function. Now, I'm more of a risk taker. Personally, what I do is I say, okay, let's find a function without realizing whether we have a function or not. Because this is telling us there is a function, so now go ahead and find it. Oftentimes what I do is try to find it. It's not very, that method that I use of just trying to find it is not very methodical. It is more for a risk-taker method, but all right, so let's do the antiderivative of this with respect to x. The antiderivative of x, that's easy, x squared over 2. Antiderivative of that with respect to x would be -xy. And this is the way I do it. Other people set it up differently. They have a constant plus a constant with respect to, which is a function with respect to y. I just go ahead and continue my work. Okay, so antiderivative of this with respect to y would be y squared over 2, which is not present. So I just keep copying down, plus y squared over 2. Antiderivative of -x with respect to y is -xy. If it's already there, then don't do anything to it. Just leave it alone. And then, so I'm done. I found a function whose gradient is going to be this. But what I do systematically is I double check that I actually got the function. So the gradient, so what is the derivative of this with respect to x? Well, it would be 2x over 2, which is x, minus the derivative of this with respect to x would be y. And then the derivative of this is 0. I'm going to put down a 0, even though it shouldn't, well, we're going to ignore it anyway, but for the record that we actually did 3. The derivative of this next with respect to y is going to be 0 minus the derivative of this with respect to y is x plus the derivative of that with respect to y would be 2y over 2, which is y. So we have x minus y and y minus x. Yep. So that means that this is our potential function. Okay. So what? All right, we want the integral of the path integral, the line integral of the field with respect to this path. Well, according to the fundamental theorem of line integrals, FTLI, all you have to do is figure out the point, the first point and the last point of this path. So when t is equal to 0, we go from 0, 0. Remember, we did draw the path. The path is this one. Starts there, ends there. So we go from 0, 0 to 2 pi 0. So all we have to do is plug 2 pi 0, the endpoint onto this equation, into this function, and then 0, 0, and then subtract the 2. So by the fundamental theorem of line integrals, all we have to do is put 2 pi quantity squared over 2 minus 2 pi times 0 plus 0 squared over 2. So this is plugging in 2 pi 0, take away 0. So now we're going to plug in 0, 0. 0 squared over 2 minus 0 times 0, because we're plugging in 0, 0, plus 0 squared over 2 again. So of course that is going to be, so that is 0, 0, 0, 0, 0, a bunch of zeros, 5 zeros. So that's going to be 2 pi or 4 pi squared over 2, which is 2 pi squared. Bingo. Same answer we have earlier as before. But notice we didn't have to do any of the sine and cosine. Yeah, we bypass the sine function altogether, the t and sine function. We didn't have to deal with that at all. Yeah, there was no sine or cosine whatsoever here involved. It was reasonably simpler. Many times it is simpler. I'm sure you can find examples where applying the fundamental theorem of calculus may be more complicated. I have to think about how to come up with them. Maybe I should do that one day. But oftentimes it is simpler to use the fundamental theorem of line integrals. Okay, let's do a second example. Oh, okay. Example 2. So the difference between example 1 and example 2, besides the fact that we're going to use different functions, is that example 2 will be a three-dimensional example. So we have a curve C defined by r of t equals, and you guys have seen this before in some of the other videos, cosine of t, sine of t, and then t over 2 pi. So, and t is between 0 and 2 pi. So we are familiar with this a little bit. It is a helix, and it goes up here. My picture is not the best, but it starts at 1, 0, 0, and ends up here at 1, 0, 1. By the time we get to 2 pi, the z value will be 2 pi over 2 pi, which is 1. Okay, so this is a nice helix, and we go up this way. All right. This line is not supposed to be there. The only reason why I drew it is so I could tell that this point, or we can tell that this point is perfectly lined up above this point, 1 unit above it. And the vector field will have 3 components, or 3 inputs, and it's a vector field, so it should have also 3 components in the output: 1, 2y, and 3z squared. Okay, so that is the field. So we're going to do this in 2 ways, with the definition. And so the goal is to evaluate this integral, the force, or the vector field with respect to that path, the integral of the vector field. All right, so we're going to use 2 methods. Method 1, okay, which means just do it by pretty much by definition. So I'm going to start squishing this here. dr equals the integral from 0 to 2 pi of this vector field. So the first component is 1. The second component is 2y. Remember though, this is x, y, and this is z. We're going to use x, y, z. Since this calls for 2y, we're going to put 2 signs. 2 sine t, comma, and then the third component is going to be 3z squared. So that means 3 quantity t over 2 pi cubed. Okay, so we got a vector with 3 components. 1, 2 sine of t, 3 t over 2 pi quantity cubed. And we're going to dot that with the derivative of this path, which will be negative sine t cosine t, and then 1 over 2 pi. Don't forget the differential. So I'm going to put an arrow since I run out of room. And there is a differential there. Okay. So now we are performing the dot product from 0 to 2 pi, bracket 1 times negative sine of t. So that is going to be negative sine of t. But the dot product is going to give us a scalar. So there's not going to be commas. That is very, very crucial. If we mix commas and pluses or minuses, it could be that we're making a conceptual mistake. It could be a typo, but it could be a conceptual mistake. I guess it depends what we do in the next step. But be careful, just be careful. It should be clear in our mind whether we are thinking of a vector or a scalar. Right now we are going to end up with a scalar because that is the output of a dot product. All right, 2 sine times the cosine. So plus 2 times sine t cosine t. All right, and then multiplying those two, we will end up with 3t cubed plus 3t cubed over 2 pi to the 4. I'm going to close the bracket, dt. Let me double check that this is, oh, I'm sorry. Here, I just realized there was a mistake here. This is correct, this vector field. Here's my mistake. 3t over 2 pi squared. Yeah, that should be a 2. You probably notice it when you were yelling at the screen at your computer or phone when you were watching that. So we have 3t squared. Yep, so this should be a 2. The exponent. And then 2 pi squared times another 2 pi, that should make it 2 pi cubed. There we go. Okay, good. Now I feel better about this. This is a scalar, this is a regular function, and we're integrating with respect to t. All right, we're going to take some shortcuts. Sine of t, well, it's a whole cycle. So that's going to be the integral from 0 to 2 pi, whether that is positive or negative. We're going to end up with 0 or negative 0, whichever way you want to think of it. This one, let's justify it a little more. We have the the integral rather, from 0 to 2 pi of the sine of 2t. And we don't have to divide by 2 because 2 sine cosine of the same variable is the sine of twice that variable with respect to t. Here, we can factor out the constants. So we have 3 over 8 pi cubed. Yep, 3 over 8 pi cubed. And then we have t squared, which we're going to integrate with respect to t. So that is going to be t cubed over 3. And we're going to plug in 2 pi and 0. So times 2 pi cubed over 3. Oh, that's interesting. That's going to be 1. That is going to be 0 because we got 2 waves. You know, this 2 increases the frequency, and we are going from 0 to 2 pi, so we got 2 complete waves of the sine function, and that's going to give us 0 as well. So we got 0 from this integral plus, and as we can tell, this is going to be 8 pi cubed. That simplifies with this, and the 3 is due to, so we end up with 0 plus 1. So the final answer is 1. Okay, so that is the first method of the second example without applying the fundamental theorem of line integrals whatsoever. Okay, so example 2, whoops, that looks funny, method 2. Okay, I'm gonna copy the r of t equals cosine of t sine t, and then t over 2 pi. 0 is less than or equal to t less than or equal to 2 pi. And then the vector field has 3 components, 1, 2y, 3z squared. Okay, so now we got the second method, which is by using the fundamental theorem of line integrals. Now, the fundamental theorem of line integrals implies we have to find an anti-gradient. Now, we could search and look, well, we can check, but, and I did not tell you how to check this, but it's kind of similar. Let's just try to find the anti-gradient. So antiderivative of 1 with respect to x. That's it. Antiderivative of 2y with respect to y, well, that would be 2y squared over 2. So the 2 simplifies, so we have to have a y squared. If the y squared was already on the first component, on the first term, then I don't have to redo it. 1 is enough. Antiderivative of this with respect to z, well, it is fairly straightforward that it would be a 3z cubed over 3. The 3 simplifies, so plus z cubed. And that's it. Technically speaking, we could have a constant, but for purposes of applying the fundamental theorem of line integrals, all we need is 1, just 1 anti-gradient. There's actually many more because we can add a constant as we do with antiderivatives, but all we need is 1, just 1. If you put plus a constant, that's not okay. That is not okay. Yeah, because the constant is arbitrary. You know, let me just pause for a moment. I think you've seen cases when we say, you know, you end up with x squared and two times the constant for some reason, and then we say, well, that is the same thing as x squared plus this constant is arbitrary, so constant 2, and then we rename the constant. And most people don't even put constant 1 and constant 2. They just rename the constant, and we're okay with that. Most of us are okay with that. So adding 2 constants gives you another constant. Oh, quite often what happens, I just remember, is that we have constant 1 plus constant 2, and then we say, well, that's the same thing as, since constant 1 and constant 2 are arbitrary, when we add them together, we end up with an arbitrary constant. Well, if that is true with adding constants, then it should also be true with subtracting constants. C1 minus C2 should be an arbitrary C3. So it isn't true that adding or subtracting constants, well, especially subtracting constants, you end up with 0. That's why when the constants are arbitrary, that's why it's not good to put an arbitrary constant on the anti-gradient or antiderivative. What you do, if you really want to add a constant, just add an actual constant like 5 or 7 or pi, whichever. And then that's going to be the same constant in the rest of the problem. And then they will subtract if you are using the fundamental theorem of calculus, or in this case, the fundamental theorem of line integrals. Be as it may, all we need is 1, so add 0 and that will do. Yeah, I'm taking way longer than what I wanted to do this problem because this is almost finished. So the line integral of this vector field over this path is going to be, by the fundamental theorem of line integrals, is going to be, oh, we need the points. Where does this start? Remember on the introduction to this example, we start here and then we ended up there. So we go from, I'm just going to make a note here, from 100 to 101. So we're going to plug in 101 first, 1 plus o squared plus 1 cubed. So 101 x, y, z, x plus y squared plus z cubed. And then we're going to subtract 100, plus o squared plus o cubed. So that is, of course, 2 minus 1, and that is 1. And that is exactly the same answer as previously here, without having to think about sine of 2t and the sine of t and all this, and even the 2 pi cubed over 3. You know, there's more. The probability of making a mistake here is greater because there are more steps than here. I'm not saying that the probability that we won't make a mistake here, the probability is smaller. Every time there's more steps to a process, the probability of making a mistake increases. Yep. Example 3. All right, this is a good example. So I'm going to describe the path first. So I'm not going to tell you the equations. I'm just going to describe it. Oftentimes we describe it when we are giving students problems to do. All right. So start at 0, 0. Go to 1, 1. Start at 0, 0. Go to 1, 1. Go from 1, 1 to 2, 0. And then go down, pretend that line is vertical. Go down to negative, or rather 0, negative 2. Okay, so start at 0, 0, go up to 1, 1, go down to 2, 0, go down and reverse to, and end up with 0, negative 2. So that's it. Start, so this is the start of the path around, and this is the end of the path. So go up, sharp 90-degree angle, turn, sharp 90-degree angle, turn, stop. So we're going to integrate the vector field 1 to y over this path. Yep. Yep. So method 1. Which is without using the fundamental theorem of line integrals. Now, notice that in the given problem, and oftentimes we will do this to students, a part of your job when we solve some of these problems will be to actually come up with a path yourself. So the method one implies finding the path. Okay, we're going to split this into three paths. C1, that's from here to here. C2, from there to there. And C3, from 2, 0 to 0, negative 1. So 1, 2, 3 paths. That makes sense. So first, we got to figure out the paths. So C1 is going to be defined by R of t. And, well, in this diagonal, x and y are the same, so we can just call it tt. And if we go from 0 to 1, we're good. So t, comma, 0 less than or equal to t, less than or equal to 1. And that will take us from here to here, under this domain for t. Okay, so C1 was not too bad. I guess we could call this R1 and R2. I'm not gonna label them because this tells us which path we're on. Okay, now we're gonna go, well, let's think about this. We're gonna go from 1 to 2. And ideally, we wanna preserve this domain because integrating from 0 to 1 is reasonably simpler for computation purposes. So we want t, and see that gets complicated because there's multiple ways of draw a path. I'm going to show you two for this path. So if we go from 1 to 2, that means we can just start with 1, add t because we want t to go from 0 to 1. While that is happening, the y value goes from 1 to 0, so it decreases. Start with 1 and take away t. From 0 to 1 for the t's. Now, I do this fairly intuitively because I can see where I'm going. But if the intuition does not work very well, then remember, this is a segment of line, and we have seen twice in previous videos how to come up with the equation of the segment of line that goes from one point to another point. What you do is start with 1 point multiplied by 1 minus t plus t times the second point, your ending point. And that is going to produce the same thing. Now, this parameterization of the path is not unique. Somebody could say, wait a minute, I'm thinking t, to make it simple, 1 to 2, except that t then is going to run from 1 to 2. And then I have to figure out, well, that has to come down. So if we go from 1 to 2, and we want to start with 1 already, you want to have 2 minus t instead. Actually, a change of variable does this. So if you want your parameter to go from 1 to 2, use that. If you want your parameter to go from 0 to 1, then use that. And you can use 1/2 instead, but then every one of the t's in here has to be doubled. So bear in mind there are many ways to parameterize a path. I'm not going to use the second one, although some people will say, well, if time goes from 0 to 1 second, don't you want the time to go from 1 second to 2 seconds? Well, yes and no necessarily. A change of variable takes from here to here without any drama. And by putting 0 and 1, 0 makes a lot of the plugging in of the numbers easier than than the 2, for instance. And the 1 also makes things somewhat easier. So I'm going to stick with this one, not this one, but I did want to show you there is more than one way to parameterize a curve. All right, so I'm going to use this again. We're going to start at 2 on the axis, and we want to end up with 0. R of t starts with 2, but we want to take away, as we go again from 0 to 1, enough so that we end up with 0. So I'm going to take away 2 t's. Yeah, that takes us this way. And then we want to start with 0 and end up with 2, negative 2. So negative 2t will do. 0 less than or equal to t less than or equal to 1. Now, things are simple enough because this is straight. All of those curves, that's funny, are straight. that's an oxymoron, a straight curve. But we generally speak about the paths as curves. So even if they're straight, we call them curves. It is funny though. Anyway, so these are straight, and consequently, these are fairly, all I'm doing is checking the endpoints. But this was curved, then we have a different story. Then we have to take into account how things curve, and then we wouldn't be so easy as just to go from 2 to 0. There will be more involved because we go from 2 to 0 in a perhaps non-linear way. Yeah. Okay. So first, we have to find the paths. Then we can start working with integrals. I just want to make sure I have page numbers. Oftentimes I forget about page numbers. So, okay. So the integral with respect to the path of the whole thing. Now, C is the entire graph, and we break it up into 3. So this is the same thing as the integral over C1 plus the integral over C2 plus the integral over C3. And the first integral, all right, is from 0 to 1 because we picked that to be the parameter boundaries of, remember the vector field is 1 comma 2y. So again, 1 comma 2y. So we have the vector 1 comma 2. In this path, y is t. And then we dot it with the derivative of the path itself, 1, 1. Oops, not equal. Just dt. So that is path 1 plus the integral from 0 to 1. Now, the reason why we're using 0 to 1 is because I'm choosing this particular parameterization. Had we chosen to go from 1 to 2, then we would use this other parameterization instead. But it doesn't matter because we're breaking this up into pieces, and then we can work with each one of them individually. So remember, the vector field is 1 comma 2y. So here we have 1 comma 2 of those, x, y. To quantity, 1 minus t, close the parenthesis of the vector, dotted with r prime. R prime, well, on the second path, r prime would be 1 comma negative 1. 1 comma negative 1. Notice that those two are different. 1, 1, 1 comma negative 1, because the derivative of this with respect to t is 1 and negative 1. dt plus the integral from 0 to 1 again, because we're going to be using this parameterization that goes from 0 to 1. 1 comma 2y, but this time y is negative 2t. Close parenthesis of the vector multiplied by negative 2, negative 2. So we got 3 integrals. Okay, let's simplify each one of them from 0 to 1. And here we have 1 plus 2t. dt plus integral from 0 to 1 minus 2 plus 2t plus the integral, so there's 3 of them, path 1, path 2, path 3, from 0 to 1, negative 2, 2 times negative 2t is negative 4t times negative 2, that is positive 8t dt. Let me double check that one because I want to make sure. Negative 2 times 2 times negative 2 is positive 8t. Okay. So we're almost there. That's going to be 1, well, t plus t squared. But we're going to plug in 0 and 1. So t plus t squared, it is 2t squared over 2, but the 2 simplify. So we're going to end up with 1 plus 1. Well, consolidating that, that is negative 1. With respect to t, we have negative t from 0 to 1 is minus 1. And again, 2t squared over 2, that's going to give us 2t squared over 2. Oh, t squared, but plug in the 1, so plus 1. Plus negative 2, well, negative 2t. So I'm pulling a fast one on you on all of those integrations. I'm doing integral of this, integral of that, integral of this, integral of that, integral of this, integral of that. So that's minus 2 plus 8t squared over 2, so that is 4t squared. But we're going to go and plug in 0 and 1, so plus 4. Okay, so that is 2 plus 0 plus 2 equals 4. Okay, so to figure out the integral over this path of this vector field, which is, by the way, very simple, could be way, way more complicated than that. We have to first find the individual paths, break this into pieces. Then we have to go ahead and do this. Technically speaking, yeah, I was going to mention that we can make one big C, which is a piecewise defined function, but then the T would have to change. Yeah, once you break it up, even if you use the same T's, I always use the same T from 0 to 1. You are going to be okay. So let's use method 2. I'm just going to sketch very quickly the. So we start at 0, 0, and we end at 0, negative 2. The vector field that we are integrating is 1, 2y. Does that have an anti-gradient? Well, let's find out. F of x, y would have to be antiderivative of this with respect to x, x. Antiderivative of 2y with respect to y is y squared, which is not present here, so we have to add the y squared. And that's it. So this is an antiderivative, anti-gradient of this. Let's double check the gradient of f. Derivative of this with respect to x, 1. Derivative of that with respect to y, 2y. Okay, so it checks. We want to double check. Okay, so the integral, the line integral over this path, so the whole thing is C, of this vector field with respect to the path by the fundamental theorem of line integrals is Oh, plug in 0, -2 here. So let's put it in 2 steps. F of 0, -2 minus f of 0, 0. Remember, this is the start and this is the end because we go in this direction. Okay, and so the function calls for whatever the x is plus whatever the y is, square it, minus whatever the x plus square the y. And that's going to be 4 minus 0, 4. Whoa. We found exactly the same answer as back here. 4, 4. With no drama, in the sense that we did not have to find any of the paths whatsoever, no parameterization whatsoever. We don't even care. And all we care about is that we start there and we end there, which means, by the way, that it doesn't matter which path you take. So if I give you for this vector, so that is what makes it work so nicely, is that this vector field has an anti-gradient. So if we start there and we end, so we're finished with the example. I'm elaborating on the value of this. Okay, so if you have something crazy like this, I just tried to write Michigan, except that I cannot put the dots because I cannot lift, in order to have a continuous path, I cannot lift the pen. But if you want to integrate Michigan, and you could have more, if I ask you to integrate 1 comma 2y with respect to the path on this curve, and this is the curve, okay, then the answer is going to be 4. Isn't that wild? So because we have a conservative vector field, and in a conservative vector field, it doesn't matter what path you take. You can go all the way, as long as we have a that's why I cannot put the eyes on Michigan, I cannot put the dots on the eyes of Michigan, because I have to lift the pen, and I try not to. So we have a continuous path, and the answer is going to be 4. Doesn't matter which path you take. You can go to the left, to the right. It doesn't matter. You can have an S. You can have, as long as we have a nice continuous path, and we start at 0, 0, and we end up at 0, -2, you will get 4. Now, if you end at 0, 2 instead of 0, -2, you're still going to end up with the same answer, because where do we? Oh yeah, if this was a 2 instead, that would work out the same way. So, but in particular, if we go from 0, 0 to 0, -2, no matter what path we take, we will get 4, because this is a conservative vector field. And in my opinion, that is super, super cool. All right, with this, we will finish this video.